Let's work on example 10.9, where we discuss the critical values underneath a normal distribution. In this problem, we have that the species of mouse that we're trying to study has an average weight of 20 grams. And we also know that the standard deviation of the distribution of weights is 4 grams. So knowing those two pieces of information, we're allowed to draw the distribution. If we look at the weights, they will be normally distributed about an average of 20 grams and a standard deviation of 4 grams. So that's what the distribution looks like. Now, what do we want to know? We want to find the 5% probability thresholds which mark significance. So if we come over to our distribution, how far over to the right do we have to move until we get only 5% in our tail? And same question, how far to the left do we have to move? Obviously, it will be the same amount because of symmetry. But how far over do we have to move until we get 5% into the left tail? And the way that we ask questions about probabilities underneath normal distributions is by looking at the standard normal distribution of z-scores that always have a center of 0 and a standard deviation of 1. And we're asking the same question, what is the point that gives me 5% there and 5% here? So in order to answer this question, let's focus on this z-score here. The table that we're given is areas to the lefts of z-scores. So if we have 5% to the right of this z-score, then to the left, we must have 95%, because we know the whole area has to add up to be 100%. So this z-score right here has 95% to the left of it. Let's go to our table. Here, this graphic tells me that I'm looking at the areas to the lefts of z-scores. So if I know that I want this area to the left to be 95% or 0.95, I'll scan through this table and look for 0.95 or a number as close as I can to it. And if you do this, you'll find that you are trapped between 0.94950, that's slightly less than 0.95, and 0.95053, right? 0.95 is right there in the middle. So what is the z-score that gives me 0.95% of my area to the left? So my z-score will be 1.6, and then halfway between 0.04 and 0.05. So the z-score that we should pick is 1.645. That would be a great estimate. So let's go back to our work. That z-score right there, which has 95% to the left of it, is 1.645. So knowing this, let's look at our z-score equation. Point minus center over standard deviation. If the z-score is 1.645, then I can find that unknown point, knowing that my average needs to be 20 and my standard deviation needs to be 4. Now, if you solve this, you find that x has to be 26.58. So that is that point right there. So any mouse that weighs more than 26.58 grams is going to be inside this significant region. The probability of that happening is less than 5%. So how do we find, let me switch colors, this z-score? Well, by symmetry, if this z-score was 1.645 and it's centered at 0, then that z-score must be minus 1.645. So if I go through this equation again and say my z-score should be minus 1.645, 0.45. What point gives me that if my distribution is centered at 20 with a standard deviation of 4? In solving this, you find that the x value is 13.42 grams. So this point right there is 13.42 grams. So a mouse that weighs less than 13.42 is very unlikely. You only have a 5% chance of that happening. Okay, so we just found the 5% probability thresholds that mark significance. Our next job is to find a mouse that weighs 12 grams. And then using that 5% as significance, is it significant? So let's just clean up all of this work. We have the weights of mice normally distributed around a center of 20, a standard deviation of 4. And the point that gives me 5% in my left tail is 13.42 grams. And the point that marks significantly high weights, which gives me 5% in the right tail, is 26.58. So using these 5% marks as significance, if we find a 12-gram mouse, then 12 grams is further to the right than that 13.42, right? 12 is somewhere right here, which means that it's in that critical region. It is significantly low. So this is a significantly underweight or underweight mouse. So we should be concerned.